maybe I have to talk a little like that, but I hope it's okay. So yeah, it was a little scary at first. I didn't know anyone that was interested in or had done that. So yeah, but at the end of 2025, we launched the company, and we are still going strong. So yeah, okay. So as we all know, the success of electrification and energy transition requires the new solutions because for energy storage, because the ones that are being used right now, they fall short. They are very expensive. They can be risky for linkages, and they are inflammable and stuff. And also there are supply chain constraints, such as I don't know if you know about lithium. There's not enough lithium, so there's a need for new materials for specifically from energy storage applications. So among these new materials, we find a lot of different candidates, but I will focus on three. First, solid state electrolytes. They are the substitutes for conventional liquid electrolytes, and they are very, very popular right now because they are not flammable, they are not volatile, and they prevent leakages. So they are much, much safer. Among them, we find polymers, oxides, sulfides, reticular materials, etc. Then we find silicon-based anodes. They are much less studied, but I think they hold great promise. So I'm very curious about what these type of materials hold in the future. They are mainly used to substitute the graphene in lithium-ion batteries, and I'm hopeful to see what is going to be in the next years. And then we find organic electrode materials. These are uh, eco-friendly because they are obviously purely organic. And as they are purely organic, they allow the customization of the architecture of the materials for specific applications. So that's very nice. The problem is that they show very low conductivity and poor energy density. Among them, we find, no se oye, ¿verdad? ¿No se oye? Ah, okay. 2D materials and also reticular materials, etc. If you may notice, I have talked a lot about reticular materials, but what are they? So first, reticular chemistry is the study of linking discrete chemical entities by strong bonds to make extended structures. The first reticular materials that were developed were metalloorganic frameworks, or MOFs, in which polynuclear metallic clusters are coordinated to organic linkers to form crystalline and porous frameworks. These materials have become very, very popular. They have been used in many applications due to their astounding properties, and indeed they were rewarded with this last year's Nobel Prize in Chemistry, which was very exciting to the field. Particularly me, I didn't expect that. So it was huge for us. The other important family of reticular materials are covalent organic frameworks, in which organic building blocks are linked through reversible covalent bonds to form 2D and 3D crystalline and porous frameworks. Today, I will be focused on this type of materials. Okay, so following the principles of reticular chemistry, in order to obtain COFs, we must select very carefully the organic building blocks. They have to be rigid and well-defined in order to maintain their shape during synthesis and allow the obtention of the desired crystalline and control framework. So, also, but carefully choosing the geometry and the size and the functionality of each building block, we can tailor and pre-design the topology, the pore size, and the functionality of the final framework. This is huge for material chemistry, because there are not a lot of materials that can be pre-designed for specific applications. So that's very, very nice. One thing that I have mentioned is that these materials rely on only on covalent bonds. Covalent bonds are very, very strong. So what happens is that While this is a very huge driving force for COF formation, it also can trap the organic building blocks in a disordered state, the kinetic product. So we don't want that. There's no order and we don't like that. So that's why the use of dynamic chemistry and reversible reactions is super important, as it allows error correction and the obtention of the final crystalline thermodynamic product, which is the COF. Okay, just a second. So indeed, in COF chemistry, the careful selection of the linkage is super important. Indeed, there are many different types of linkages. The first one that were studied were boronic esters and boronic acids, but these type of linkages are prone to hydrolysis in the presence of water, so they are not, I don't really love them. The other important family of linkages are imine bonds, and these are the most widely used because, for one, we have a lot of possible building blocks, many different amines and haldehydes of different topologies, sizes, but also they lead to very chemically and thermically stable COFs. So that's why they are widely used. Furthermore, there's a lot of different synthetic conditions that can be used they are very versatile. So there are many different conditions. Typically, among these conditions, in order to achieve this reversibility of the covalent bonds, there's a need of long reactions times, high temperatures and pressures, organic solvents, and even anaerobic conditions. That's why the solvothermal synthesis is the most used approach. Nevertheless, over the last years, different alternatives have been developed, such as the hydrothermal synthesis or many room temperature ones. Among them, I will love to present you this approach, which for me it's amazing. It was developed by my former group, Felix Zamora Group, at the Universidad Autónoma de Madrid, and it allows the obtention of stable COF nanoparticle suspensions, colloidal nanoparticle suspensions in water and room temperature for the first time. It is in this methodology, the surfactants allows the solubilization, the complete solubilization of the organic monomers in water, and also the formation of micelles that act as nanoreactors, preventing the growth or the excessive growth of the nanoparticles. At the end, we obtain nanoparticles that are around 20 nanometers in size, and they are homogeneous. Also, the production of these nanoparticles allows for a great surface area. And the isolation, the wonderful part is that the isolation of these nanoparticles can be easily achieved by just changing the pH or adding a non-solvent, such as an alcohol. So this work is outstanding. Then, following this work, another one was developed by your group, former group. Excuse me, I'm not used to not being part of my former group. I'm still processing. I'm outside of that, of academia. So these colloidal suspensions could be modified in order to obtain coffins that could be printed by a microfluidic 3D approach. You may think that this is trivial, but it is not. It was the first time that a COF was 3D printing without the need of an additional binder or support. They were pure COF monoliths of different shapes and sizes. When we saw that, we thought, okay, this is very promising. We could obtain electrodes for energy storage, but the problem is that COFs are not typically conductive. So how about a composite? I did my PhD around that. What can we do? Indeed, COFs are amazing materials, but they suffer from some limitations. They, for example, so low conductivity, but also poor dispersibility, insolubility, hydrophobicity, and poor processability. The other ones were solved mostly with this 3D printing approach, but we needed to overcome the low conductivity. So we thought about incorporating another functional material. Indeed, COF composites have been widely explored. There's a lot of different materials that have been incorporated, but in terms for energy storage, mainly 2D nanomaterials are the go-to. So we decided to start there. We incorporated graphene to obtain a nanocomposite that could potentially have even better properties than individual components. So we wanted to see if there was a synergy between both materials. Our idea was to obtain electrodes for supercapacitors. I don't know if you are familiar with this type of devices, so I will briefly introduce them, but they are like a bridge between conventional capacitors and batteries, and they are formed of two electrodes of high surface area that are separated with a thin dielectric layer. Typically, batteries retain energy or store energy by electrochemical reactions. That's not the case for supercapacitors. They store charge in the surface of the electrodes. What this does is that they deliver ultra-high power, very fast charge and discharge cycles, and long cycle life. So they are very promising nowadays for energy storage applications. The problem is that these electrodes are expensive, both in the materials that are used, but also in the production. So lowering the cost of these electrodes is very, very important. Furthermore, the materials often used are metal-based, which are not ecologic, and as I already mentioned, they suffer from supply chain constraints. Sometimes there's no more metals available, and that's a huge problem. So also the other alternatives that are carbon-based, for now, they exhibit quite low performance. So new eco-friendly alternatives are super desired. Finally, nowadays, the technology doesn't allow customization and the specific design for applications. So that was also a point that we were interested in addressing. Okay, so what was our idea? Combining functional materials with our technology. In our case, the organic framework, the covalent organic framework, thanks to its porosity, favor the mass transport of the charge. And then graphene incorporated the conductive properties and the excellent mechanical properties. What we saw is excellent electrochemical behavior due to the synergy between both materials. Indeed, by mixing the advanced materials with our 3D printing technology, it's worth mentioning that everything is patented with patents all over the world, in Europe, Japan, China, and USA. So what we obtained were 3D printing graphene nanocomposite electrodes that could be assembled into next generation supercapacitor devices. Okay, so in the end, what we saw is that this technology was cheap and scalable. We are working still on that, but and allow the production of cost-competitive next generation devices. Indeed, we observed high capacitance, over 230 faradays per gram, which is huge, very good energy and power densities. The electrodes were purely organic, so no metals are used, and the manufacturing process is also green. There's no need of organic solvents, none of that, so that's very nice. Furthermore, these electrodes, as you have already seen, they are customizable, and we can adapt the shape and the size to to the needs of the clients, and they are very, very lightweight. Consider that we only are using carbon, nitrogen, and hydrogen, so they are very lightweight. I'm talking about almost 40 times lighter than a commercial one. So that's very, very nice. Is this market relevant? O sea, I mean, where we can use it, someone is going to buy it for sure. This market of the graphene-based supercapacitor market is growing very, very fast, around 20% each year, and is expected to reach $20 billion in the next decade. The markets that are mostly driving in this direction are China, USA, and Europe is going, I promise. But yeah. And in which applications we think that, and we are working to enter and to go in markets where there's a need of a rapid energy delivery and where the weight is critical. As I mentioned, our device electrodes are very, very light. So in applications where the weight is very important, we can stand out. Also, where there's a need of energy peak control. So I'm talking about automotive applications in case of using the extra energy of in the generative braking systems, but for sure in aerospace. We are really focused on this one, on drones and UAVs. And finally, in electronics, such as portable devices, such as smart cards, phones, etc. Okay, so I'm almost finished, I promise, but just a quick recap of what where we started and where we're going. I don't know if you're familiar with this, but we are in a tier 3 to 4. Our technology has been validated in the lab, and we are working in the next years to a tier around 6 to 7. That's okay. I will talk a little then later about that, but. So we were funded with a pre-seed round at the end of 2025. And then what we are doing now is improving a little our electrochemical performance to be ready to enter the market. And we are looking for market product validation, just the help of other companies to test our devices and say they are good. Okay. And pilot agreements. The objective is to obtain an MVP. That is a prototype, let's say, and that could position ourselves in a year or 6 to 7, and that's the hope for this year, approximately. And we are seeking also for now public investment, but then funding, and then also private funding. Okay, so for the next years, first we will seek commercial consolidation and early industrialization with certifications and such, and then we will proceed to industrial scale-up and market expansion. Just to end, I would like to present my team. I'm very proud of them. So apart from me, that I'm here wasting your time, we have our lab tech, which is amazing, as she will be joining us as an industrial doctor, PhD, and doing the industrial PhD in the company. And we are, in the next months, we will hire a CTO. Also, as I've mentioned, we also have excellent technological advisors, such as Felix Zamora, Sergio Royuela, and David Rodriguez San Miguel, that were also in charge of developing the technology for this company. And I would like to also mention the funding received by Grow Venture Partners, which is a venture capital firm in Barcelona that helped us with the pre-seed round and made possible that the company started. So that's all. you have any question, curiosity?
Which material you use usually for the electric?
There are a lot, but sometimes what we typically use is glass fiber. There is very thin and like a very thin layer. It's we're not especially what we do is for now is not like the assembly is just for the testing. What we fabricate is the actual electrode, which is the active material. The rest is bought, and we do the assembly just for testing the electrodes. In the future, we will see. For now, we are just hoping to sell the electrodes, and somebody else is going to um, assemble them in the device. Maybe in the future we can develop the technology like a specific electrolyte, a specific the electric, a specific. For now, let's stay with the electrodes that is hard on itself. Yeah. And typically, it depends of the cell. Like if it's a coin cell, we typically go to spheric. I don't know if I'm saying correctly it is in English, but a spheric electrode. Yeah. But in I don't know if you're familiar with pouch cells, but they're usually rectangular. So it depends. We are transitioning from because we are interested in the pouch cell format, but we haven't tested that yet. So we are working on developing rectangular electrodes for that purpose. Because as I don't think I mentioned, but our mechanical properties are very, very good. So in order to benefit the most of these mechanical properties, like the flexibility and such, pouch cells are much a very good approach. Mm-hmm.
You said like amorphous,
Mm-hmm.
and you correct the arrow and to make it crystalline.
Exactly.
So, I mean, how do you correct the arrow in the from amorphous?
It characterizes the fun part of COFs is that there's I can tell you about it later, but there's a very beautiful research paper of Dictel, which is an American researcher that discovered that they correct the structure by themselves due to the reversibility. So it's like forming and breaking bonds till it reaches the. That's why the reaction times they are almost quite long because the structure needs to the bonds need to break and form until it reaches the thermodynamic structure.
So, I mean, the crystalline structure is the stable structure for it.
Exactly. Exactly. I could talk a lot about COFs. Yeah, that's my expertise. So if you want a later, I can talk about it. No. Well, DLS, yeah. Oh,
Yeah.
what?
TRL, like technical readiness of your product.
Exactly.
So, is it like 6-7 is expected, or are you done?
No, we are working on it. We are working on in an MVP. In maybe in the next, like in the next, I hope in the next 6 months, 6 months we are there. We are. There's still a lot to change.
Time what's it called? Maximum.
Exactly. But yeah, from there, there's yeah. Um, the curve is very high. So yeah. Okay.
Which is the minimum size that how we can grab it?
That's a very good question because right now we have talked to other companies in order to get feedback, also to align or research with the needs of the market. Now we are not in the lab. Now we are in the real world, and I thought, for example, that capacitance was the most important thing in the world, and companies were like, "No, it's not." and you have to redo or rethink your research, so or your tech development. So in there's a huge need of very small devices, and also very thin. So in our case, what we can do is very thin uh, electrodes around 40 to 50 microns. There are people that are doing even less, uh, but it's a problem in order the mechanical properties get compromised, obviously. So we are working on doing them thinner. But we are in the future, we will be very interested in doing very small, because we know people that companies that are interested in putting the devices in water bottles, and I don't know exactly why, but they want them in everywhere. I don't know. I think they wanted a sensor there with testing whatever, and they needed a store energy, but very small, because they wanted to be in the yeah, exactly. So
They will achieve the limits of utility.
uh, not exactly. What we do typically is we obtain the monoliths, the that are the composite, and then it's just by compression. We can control like the thickness in the 3D printing, but also the amount of compression that we do with there's a specific machine that does that. So it's like a game between how much you want to compress it, because you are also limiting, like reducing, not a lot. You have to compress a lot, but you reduce a little the surface area, the macro pores of because I can talk a lot. So you, if you want, you can stop me. But the macro there's a hierarchical porosity in the monoliths. There are micropores, mesopores, and macropores. The macropores maybe through the compression can be gone. So it's it's tricky, but yeah, there's a compression part. The graphene is integrated in during the printing process. I don't I can't talk about the specifics, but yeah, it is fully integrated, and we also can control how much we add, if the distribution is homogeneous and stuff. But it's during the printing process. I'm sorry, I cannot give more details about that. Now I'm not in academia. I can't talk about that, but it's very interesting.
Yeah, makes sense. So when you are no, you're transitioning from the
Yeah,
university to the real no.
yeah.
So
It's
which are the
hard.
main challenges that you need to face?
Mm, the first one is the change of mentality. Um, in you have to be very I don't know. I don't want to be rude to anyone, but in academia you have to be super sure that um you have the result already in order to to explain them, or to do a research paper or whatever to publish them. But in a company, like sometimes it's almost there, but they are already saying, "Oh, we got it. It's all." And I remember with the investors saying, but we don't have that yet. And they were like, it's okay. When they are interested, you already will already have it. And I'm like, yeah, but right now I don't have it. So how can I say that? And the changing mentality of, I don't have the data to say that. Um, and I'm still struggling with that. I'm still also, like I said, some parameters that are key in academia are not key in the market, and that's was for me eye-opening. Like, we're working for excellence in this area, and they are insisting in other things that we don't know nothing about. So it's hard. It's hard for sure. But I'm very happy. So I encourage you. It's a journey. But I encourage you that there's another option post PhD that is not a postdoc. There's other options. Risky, but other options. If you feel like academia is not your place. But sometimes I was done with my PhD. I knew I was very proud of what I did, but I needed other stuff.
So you were talking about, now you're going to plan, no, you're planning to do a prototype, no,
Mhm.
next month. And no, what about next? So what is the plan for scalability? Do you think that your technology can be reached, at an industrial level, no?
It's hard because I'm a chemist. So in the future, we will need an engineer, a chemical engineer, um, because yeah, if in order to obtain the inks in liters, that's gonna be a whole new chapter, and then um, we activate the monoliths with a supercritical CO2, which is is a fascinating technique, but scaling that up will be also a challenge. Um, Doing parallel impressions, like many electrodes at a time, it will take yeah, for sure, it will be a journey. Yeah, ahead. Yeah, we have a lot to work on.
Okay, so right now, no, what do you think is the real bottleneck today? No, materials, cost, scalability,
Cost.
the cost.
For now, till we reach a point where we are we have scale up and find cheaper building blocks and stuff. For now, is this cost. We are thinking in a premium device for a specific application in which the weight is very important. But even though it is premium, nobody's going to pay that much for a device. So we are working on that. Yeah. Ink, because it has the viscosity and the rheological properties to be printed. It's a terminology. It's not. Hmm.
Okay, so just no, okay.
Mm.
Given that the mechanical properties of the electrode was so critical,
Mhm.
is there any possibility of application bendable devices, flexible, for example, nowadays that it's really a tricky question of developing flexible mobiles.
Mhm. Yeah.
Do you think that it's going to be a
It's tricky. Like the thing that is going, like I mentioned, the pouch cells are like the first step in that direction. I don't know if we could reach much more after that. Like I don't need the whole information in that matter to answer you properly, because I'm still learning uh, about this. Um, it's very hard. It's very hard. I remember in one paper that we had to do, like the referees asked for measurements of different electrochemical measurements with different flexibility flexion, and just the technology to measure that, it's like we didn't have the equipment to do that. Like it's very hard to like there's many, I think, years to go in that direction, but it would be super nice. I mean, that'd be super cool.
Final advice for the students who maybe want to create a spin-off uh, in the next future?
Like it's almost the same as everything. You have to learn to a lot of stuff quite quickly. But yeah, you have to be a little brave. But if I can do it, you obviously can. And yeah, it's very, very rewarding. And I'm with Samantha in the lab, and it's almost the same, but not really. So it's kind of a different approach to research, but it's exciting because it's our little project, and yeah, it's almost the same but different than a regular PhD or project. So it's very nice. It's another thing to consider in the future, for sure.
Thank you very much, Anna.
Thank you, guys. Thank you, guys.